Yep, thanks very much. So yeah, I'm going to be talking to you about mDBC for general purpose SPH. So just a quick outline of my talk, some motivation, so I want to do the work. I'll then go over the methodology of mDBC, then some results, which I'm going to show you some still water, a sloshing tank, a 3D dam break, and then a fish pass. And then it's going to end with some conclusions and future work. So just some brief motivation. Obviously, we all know that boundary conditions can be quite difficult in SPH, and they've been highlighted as one of the grand challenges of SPH by Spheric. And because of this, there's quite a few different approaches. One popular approach is called dynamic boundary condition, or DBC, and this is currently used in the Joules physics code. And so for this boundary condition, if you have your fluid, which are the blue particles, and then the green are the boundary, and then the black line is the interface between the two, what we do is we update the density of the boundary particles through the conservation of mass, exactly the same as you would the fluid particles. And then the velocity of the boundary particles are just set to 0 for a stationary boundary. So the advantages of this method, it's highly computational efficient. It's quite nice because you're using the same equations for both the fluid and the boundary for your density. It has an ability to deal with very complex geometries. Anybody who's used Joules physics knows you can create quite complex shapes and quite complex geometries. And through that, it can be used for real engineering problems, which is really useful. However, there are a couple of disadvantages, if anybody who's used DBC will know. First of all, you can get unphysical density pressure values in the boundary, and they can be quite noisy. And also, for certain resolutions, you can get this gap forming between boundary that's been unsubmerged as fluid then goes to hit it, as you can see in this example. So our solution is modified DBC or mDBC. And so basically this, the aim of the boundary condition is to fix the issues highlighted while still keeping as many advantages of DBC as we can. So this is to get a smoother pressure or density in the boundary and to try and remove the gap. So we're still going to be using the DBC boundary particles. So this ensures we can still create a nice complex shape geometry. And what we do then is we then create some ghost nodes in the fluid domain to get some fluid properties from there. And to do this, we use the approach of Tafuni et al. For inlet-outlet boundaries, which is currently included in Joules physics. And so it means if you're using an inlet-outlet and mDBC, you've got a nice consistent boundary condition all throughout your domain. So just a quick overview of the method. So again, we've got our fluid in blue and the boundary in green. And so we use a mirroring procedure based on the approach by Moroni. So for each boundary particle, we find the normal to its boundary. And using this, we create a ghost node in the fluid domain and then do a SPH sum around that ghost node over the surrounding fluid particles. Okay, so at that ghost node, we can, as you can see, this summation is truncated because we've got the boundary next to it. So to fix that, we use the approach of Lewin-Liu to retrieve first order kernel and particle consistency. And this involves forming these equations. So this is going to be 4 equations and 4 unknowns. In SPH form, the equations look like this. And so our 4 unknowns are the FG and the FG comma beta, which are the gradients of FG in each direction. And then all of the sums here are found through that SPH sum at the ghost node. So we find those, that's quite easy to do. And so through this, we then end up with a linear system of 4 equations with 4 unknowns, where B and A are the summations that were found at the ghost node. And so we can quite simply invert the matrix A to then find F and its derivatives. So we use this for our density. So what we do is we get to get the density at our boundary particle, so rho B is then found by the density rho G at the ghost node. And then we use a Taylor series extrapolation using the gradients and the distance between the particles. So this work, I'm just pointing out now, was a bit of a collaboration between Manchester and the University of Vigo and Parma with the Joules physics teams. And through this, mDBC has been now included in the latest release, so version 5 of Joules physics. And a lot of the examples we're going to show you now are included in the code as examples there. And if anybody would like to see any more information about mDBC or the results, have a look at our paper, which was published not long ago. So on some results. The first one is the still water, classic test case for SPH. So on the left, we're going to have the DBC result, and on the right, we're going to have mDBC. And then we've got two resolutions. We've got a quarter resolution on the top and a final resolution on the bottom. So as we play the video, you can see that mDBC settles down much quicker, where DBC, the particles are still moving around a little bit, which is pretty typical of DBC. If we now zoom in on the boundary themselves, you can see we've got a much smoother density or pressure colouring through the boundary particles, and again, the fluid particles aren't moving around quite as much. So if we now plot the pressure against the depth, so this is normalized pressure against normalized depth. So the red dots are mDBC and the blue dots for DBC for each of the particle spacings. I think we can quite clearly see that mDBC improves the how noisy the pressure field is. It gives a much better approximation of the hydrostatic pressure through the depth. And so I think this shows we can improve the pressure density in the fluid and in the boundary. And if we also look at the kinetic energy, you can see that again the red line for mDBC is much lower, so the particles aren't moving around as much, which we saw in the video before. So our next example is a sloshing tank. So here we have a sensor on the left. It's got sensor 1, where we'll be measuring pressure later on, and the tank sloshes back and forward around the central point, which is a black dot in the middle. So here's a quick video. So as you can see, we've got mDBC again on the right and DBC on the left. And so what you can probably see with the top videos is there's still the gap forming with DBC, and that's disappeared with mDBC. And the pressure in the boundary is much smoother. So if we zoom in on the boundary again, you should be able to see immediately the gap has disappeared or has been reduced quite significantly. And this can be definitely seen with the second impact that comes across. Again, the pressure at the bottom of the boundary is much smoother. So I think we can safely say we've removed the gap, which is really good. And so anybody who's used Joule's physics and DBC knows that if you want to get a pressure result from this, you can't just place your pressure probe on the boundary. So here we have the pressure probe placed on the boundary as we'd expect from the experiment. If we plot this against the experimental results, so the black line here is the experimental pressure, and the blue line is the pressure from DBC with the probe on the boundary. You can see it doesn't agree very well at all. This is because of this gap forming next to the boundary, preventing you getting a measurement. So to overcome this normally with DBC, you'd have to move your probe into the fluid by a distance, normally around a smoothing length. Which would then produce this green line, which, as you can see, gives a much better agreement to the experimental data. However, with mDBC, we can keep the probe on the boundary, so it's exactly where it would be in your experiment. And this is the result from with the red line. And as you can see, we're still matching the pressure while having the probe in the correct position on the boundary. So I think this is quite good for comparing to experimental results. You don't have to worry about moving your probe in a distance or anything like that. So our next result is a 3D dam break. So this is just a test that we can still, the boundary condition works in 3D with a bit more complex geometry. So to play the video, you can see on the top with DBC, there's still the gap between the obstacle and the water as it comes down, whereas with mDBC, the gap has disappeared, which is really good. I think we can say we've removed the gap in 3D. If we now look at some depth results, so here we were looking at the depths at H3 and H4, which are in the center of the tank, just in front of the fluid column and in the fluid column. And so DBC does quite well in the fluid column, but I think mDBC, I think they both do pretty well with the depth. But if we look at the pressure again, so this is measuring the pressure on the surface of the obstacle. Again, the blue line is with DBC with your pressure probe on the surface as you would expect with the experiment. And you can see again, it fails to measure the pressure. Whereas with mDBC in the same location with a red line, you can see we're matching pretty well to the experimental pressure. So again, we've improved the pressure and density in the fluid and the boundary, and this is in 3D. So our final test case is a fish pass. So we wanted to do this to see how complex a test case we could have. And We've got a number of walls blocking overflow, which as we let it run, you can see the flow goes over the weirs or through the gates. And I think this is safe to say we can do a complex shape geometry, which is one of our tests. So from this, we were comparing some experimental results from the University of Parma. And so as you can see, we've got a number of walls blocking the flow. Each wall has a weir and a gate, and they alternate. So if you've got a gate on the left-hand side, the next wall, the gate will be on the right-hand side. So through the experiments, there was quite a number of results we could compare to. For the paper, we just worried about these 5. And so in a numerical model, we have a inlet zone at the top and an outlet zone at the bottom using the Tafuni approach. And we're interested in this zone here, which is going to be pools 1 and 2, and then walls 2 and 3. So hopefully this will make sense in a second. And for this presentation, I'm just going to focus on these 2 results of the 5 that we looked at. In each case, the simulations run for 10 seconds of physical time, allowing to reach steady state using for both DBC and mDBC. So this first plot is for the water depth in pools 1 and 2 for the gate only flow, which is the first one we're going to look at. And so in each case, the black line is the experimental expected depth, and then the darker colored lines are for DBC and the lighter colored lines are mDBC for different particle spacings. I think here it doesn't really matter which boundary condition you use. They seem to be pretty consistent between each one. As you can see, the dark blue and the dark green and the dark blue, both green lines and both blue lines kind of follow each other, and it's more dependent really on particle spacing. And if we look at the flow rate through the gates, this is through gates 2 and gates 3. Again, the results match pretty similar. They're all pretty similar and working together. However, if we look at the weir flows, so this is again the depth. So if you compare DBC to mDBC for each particle spacing, so this is the light blue to the dark blue, or the pink to the red, you can see that the lighter colored lines agree much more to the experimental black line. So it shows that mDBC is a big improvement over DBC. And again, if we look at the flow rate over the weir, you can see quite clearly that the light blue and the pink lines for mDBC are much closer to the experimental prediction. So quickly some conclusions. We developed an improved version of DBC in Joule's physics, which is a combination of the Tafuni et al. Extrapolation and Moroni ghost nodes. This is running on both CPU and GPU, and it's currently been released in version 5 of Joule's physics. And so we then tested this against a number of benchmark test cases and experimental cases with, I think, clear improvements over the original DBC method. Let's remove the gap. We've got more physical pressures in the boundary. And I think we've kept all the advantages of the original DBC, such as creation of complex shape geometries. So some future work. We'd like to extend mDBC to include a more accurate no-slip or free-slip condition. At the moment, the velocity in the boundary particles is still just 0. We've got some preliminary work at the moment on this, just for some simple flows. So the red dots on the right is for mDBC with a no-slip condition, and you can see there's a much better agreement to the psi flow profiles. And then we'd like to test this on larger 3D test cases or real engineering applications. Yep, that's all. Thanks for your attention.
Thank you, Aaron. So, I mean, as somebody who's made extensive use of Joule's physics over the years for various different types of problems, I mean, the things that you've effectively fixed with this improved method, you know, very, very welcome. That pesky gap in between things, for example. I do have a question, but at the moment there's a couple of other questions. So there's something in the Q&A, and then I'll come to you, Richard, if that's okay, after that. So in the Q&A, there's a question, 2 questions from the first from Mashi Green. So I'll just read it out. It's very in depth. But first of all, good job improving DBC. I agree. I have a few questions. In the still water cases, did you use artificial viscosity density diffusion? And have you looked at total energy? The reduced kinetic energy alone could also point at over-dissipation. And is the physical boundary between the fluid and wall particles or on the wall particles? And do I need multiple layers of wall particles, or could it work with just a single layer? I intend to test them myself in the near future, so it'd be good to know what to expect. So there was 4 questions in one, in effect, but you can read them, so hopefully you can answer them as well.
Yep. So in terms of artificial viscosity density diffusion, yes, we're still using artificial viscosity in this still water, and I think we did test it without density diffusion, and I think what I've just shown you does have density diffusion in it. But you have to read the paper to make sure, but it does work with and without density diffusion. We didn't look at total energy, we only looked at reduced the kinetic energy. It could be something we could look into in the future. That's a suggestion. The physical boundary, so if I can share my screen again. The physical boundary is it shared? Yep.
Yep.
Yep. So for this for the sloshing tank, if that's all right. So the physical boundary is this black line or the interface between the two. So here the red particles are your boundary particles and the blue are your fluid. And so what you want to do is define your geometry. So this black line here is your interface or your physical boundary. And yes, you need more than one layer of boundary particles. What you want to do is have enough boundary particles so your kernel support for a fluid particle near the boundary is complete. So in this case, I think there's going to be 4 layers that are then going to generate the normals to get the ghost nodes. I hope that helps, Mashi.
You're muted, Stephen.
I know. That's the first time I've done that in a long time. So, seems to be positive responses coming back from Mashi in the chat, Aaron. So I think you've answered his question.
Good.
Okay, so I've got 2 more questions. So if you don't mind, Richard, as one more to stay through the Q&A.
Going with expert questions. Yeah. I'm going to ask usual non-expert question.
So there's a question in the Q&A from Paul Gronenboom. And again, it's 2 questions really in one. So how does the new method affect the CPU or computational load, I should say, because obviously Joule's physics is both CPU and GPU enabled. Yeah. And did you consider the possibility of replacing boundary particles with direct ghost particles, having the mirrored position and velocity, but no displacements?
So in terms of numerical cost, it's about a 10 to 20% increase in computational time, depending on case and hardware and so on. We did test it with a number of GPUs and I think at least 1 CPU. Again, more details are in the paper if you'd like to have a look at that. Consider the possibility of replacing boundary particles. I'm not sure I quite understand the question. Sorry, Paul. But okay. Yeah.
I mean, it's quite the downside to these webinar formats is it's hard to have a 2-way conversation. So perhaps that's something you could take offline by email, perhaps.
Yep.
If that's okay, Paul. Right. Okay. So another's just come on the Q&A. However, I've deferred you for long enough, Richard. So I'll go to Richard next, if that's okay, and then we'll ask our next Q&A question.
Yeah, I really loved that. That was fabulous to see. I'm really encouraged. As a non-expert in astrophysics, the universe has no wall in it. So it's very lucky for us. So it's great to see you can deal with the walls. Sometimes the results were not exactly the same, though, as the experimental results. Is that down to this slip, non-slip behavior, or are there other limitations?
Without rerunning them with a no slip or a free slip condition, I'm not sure I can say yes or no, but it's certainly interesting to rerun some of the things with a proper no slip condition.
Yeah.
I think it should certainly affect the fish pass, for example, because you're going to have many walls slowing things down where it's not currently happening.
Yeah. Yeah, very interesting.
Yeah, thank you.
Okay, Richard. Right, so there's another question then in the Q&A from an anonymous attendee. So amazing progress on SPH conditions. When I use Joule's physics to simulate 3D pipeline flow, I often get warnings that some boundary particles have been excluded. For the boundary conditions of the curved surface, will the new method work like a plane, or do you have any suggestions on how to improve that?
So you've got boundary particles being excluded. I would suggest you check the main definition right at the top of the XML. It sounds like you've maybe set that a little bit too small, and you're getting some particles just being generated just outside, so they'll then get deleted. Hence your warning. Excuse me. Yeah. For the curved surface, it should work. I believe there are a couple of issues at the moment with generating some circular geometries. I think people are working on that. I know Jose's been working on GenCase quite a lot recently. So for the cases I've used where I've got a circular geometry, it works quite well. So long as you can define the interface to mirror across and you've got your particles in the right spot, it works fine. But it may take it a bit of tinkering just to make sure your curved surface is exactly what you want. And again, make sure your domain's big enough so you're not excluding any particles.
So I think that probably refers to some of the conversations you've been having with one of my colleagues in STSC recently, where there seems to be some problems generating normals with curved surfaces. Using the automatic normal generation capabilities of the pre-processing tool, probably it's better to define. So if you were to manually generate the normals, I don't think the problem would be there.
Yeah, exactly. Yeah, if you're willing to go into the code a little bit and manually generate it, I believe there are some methods to manually set your normals in the XML, but I've not used that. I prefer to use the HDP approach for anybody who's used mDBC, where you draw your domain out and then hit your particles outside. I much prefer that way.
So known issues that clever people are working on.
Yeah.
Okay, and we have a follow-up question from Mashi as well. The advantage of DBC of capturing complex geometries was related to the ability to use a single layer for things like a thin plate, for example, a propeller blade. Could you possibly use the same method by obtaining the normals from the fluid side? So, for example, Sun et al. I'm not aware of that one, but shifting using the eigenvalues of the correction matrix. It's an interesting idea.
Oh yeah, I don't think I've read that paper, to be honest. It's quite a good idea, that actually. It's not something we've thought of. I think we've kind of thought mainly for having multiple layers as much as you can. Yeah. So if I should just put in the chat for me, we'll talk about it in person.
Yeah, I can certainly see the potential benefit of that. As Mashi said, one of the key benefits is this ability to capture complex, thin structures, and if you sort of if you're able to maintain that capability as well, then it's kind of like the ultimate boundary condition. Yeah,
I think for the fish pass, I think the walls were like 4 particles thick. Was for our course's resolution. So I think again, so long as you're I think with the propeller, you can probably have multiple normals pointing out if you've got a couple of layers, and have the normals pointing in opposite directions of the turbine, if that makes sense. So that could still also work.